Hi there, this is Dr. John, your physics and math professor, coming to you with another circular motion problem. This one is the Ferris wheel, which is a very common problem. You're going to have this on one of your tests, for sure on one of your assignments, so let's go over it together. Here we have a Ferris wheel, which is the most horrible ride at the entire fair, and it has a radius of 10 meters. That is from here, from the center to any of the buckets is 10 meters. It goes around one full revolution every 20 seconds, and there's some children on board here, each with mass 35 kilograms. And we want to calculate two things. One is what is the normal force at the top and the bottom? That is, the children are sitting in these buckets and the buckets are pushing up on the children with a certain force. What is that at the top? What is that at the bottom? Now it's probably going to be different. And what speed is required so that the passenger at the top will feel weightless? Now to analyze this, we're going to need a couple of different things. And obviously, since it's circular motion, we're probably going to need our mv squared over r. Let's just take a look at that here. We're going to need m, well, we have the mass of the child, v squared over r. We have the radius that's given to us, but we don't have the velocity of the Ferris wheel, so we'll need to calculate that. Here I've drawn the same Ferris wheel image here, but without the buckets on it, and we're told this, that it goes around one full revolution every 20 seconds. We want to find the velocity. So the velocity is going to be equal to the distance divided by the time. What's the distance it goes? Well, this all the way around a circle is called the perimeter, and that's 2 pi times the radius. So 2 pi times the radius. And what's the time that it goes around all the way? That's 20 seconds. 20 seconds over there. Well, we know what r is. R is 10. So let's plug r in there. And we have 2 pi 10 over 20. Well, 2 times 10 is the same as 20. So we're just left with pi here. It's an unusual term for the velocity, but they use it this time, so we're just going to use that, and hopefully that'll help us in our calculations. So I'm going to write that up here somewhere, and that is the velocity is equal to pi. So we just calculated that. Now let's look at this next term here, this mv squared over r. We know we're going to need that at some point, so let's calculate that as well. mv squared over r would be equal to, well, we're going to use this child, since all the children on the Ferris wheel are going to have the same mass. And v is going to be pi, so we'll square that over r. R is going to be 10 again. Now we're going to have this number here. This is going to be about 10, so that's going to be about 35 altogether. I actually get 34.5 newtons. So that's the centripetal or centripetal force, which would be the force that you would need to pull inward to continue to cause this circular motion. It would also be equal to the centrifugal, or the sort of simulated or fake gravity that people will feel in the outward direction as well. I'm going to write that up there as well. Force centripetal is going to be equal to 34.5. And there's of course going to be another thing that we're going to need, and that is the weight of this person, which is going to be m times g. So 35 times 9.8, I am getting 343 newtons for the force of gravity. So here's the different thing. This is the force of gravity, which is just mg. This is m v squared over r, and that's the velocity. Those are some components that we're going to need as we go on in our calculation. I'm just going to do a sort of a repeat of some of these things here so that we can see what's going on, and then I'll come back. Hold on for a second. Okay, I am back. I've drawn this cool little sketch. So I've tried to duplicate the sort of top bucket, partially pink. That's the pink seat. And this is the blue seat here in the bottom. Now what's going to happen to these people as they go around? Remember, as they go around like this seat here, this portion here is going to have to be accelerated or pulled toward the center here with an acceleration equal to v squared over r. It's going to have to be pulled this way continuously to allow it, of course, the struts, the thing that holds this together is what's going to pull it together, but it's going to have to, this seat's going to have to experience an acceleration in this direction. And the same thing over here, this thing's going to have to experience an acceleration in this direction here. So now just think about this for a second. Remember the picture of the elevator. So here we have your classic elevator, and we have this person standing on a scale in the elevator. And when the elevator is not moving, it has no velocity, or it has a constant velocity, they're going to see their weight, and it's going to be mg. Of course, I'm going to list it here in kilograms, but it's really going to be kilograms times g. So it's going to be 50 kilograms. Of course, you should multiply that by G. But we see our scales in kilograms, so I'm just going to list it like that. So they're going to see their weight as 50 kilograms. Now, what happens if the elevator accelerates upward? Well, if the elevator accelerates in the upward direction, it's pulled upward, suddenly this person is going to feel like they're pushed down with an additional weight, with an additional push. So now they're going to have mg plus acceleration. So if the elevator is accelerating upward, say at 1 meter per second squared, and of course gravity is 9.8, so now they're going to feel 50 kilograms times 9.8 plus 1. Their apparent weight on the scale is going to increase because the elevator is accelerating upward. So in a similar way, right here, I'll just erase this so I'm not so crowded. In a similar here, this bucket at the bottom is accelerating upward. So this person here is going to feel a heavier weight. In other words, the seat is going to have to push up more on this person to compensate for the fact that this person feels a heavier weight. So here, the normal force is going to be equal to mg, which is this child's weight, plus mv squared over r. This is the weight that we did right here, the force of gravity. I'll just write that in there, force of gravity. And this one is going to be Fc. So you're going to have the force of gravity, this person's going to feel, plus it's going to feel like they're heavier because their chair is being accelerated upward under them. So this is going to be mg plus mv squared over r. And similarly in the top, they're going to feel lighter. Now you know this by experience. I'm just trying to sort of give you the mathematical justification for it. It's going to be mg minus mv squared over r. Fortunately, we've already done these couple of calculations. We can just plug the numbers in here and see what becomes of it. So the force of gravity for these is 343, and here we have to subtract 34.5, and here we have 343 plus 34.5. Here we go, I've done the quick math on my calculator. This one is going to be 308.5 newtons, and this one's going to be 377.5 newtons. I haven't considered significant figures yet. Let's do that now. Here we have two significant figures. Here we have two. I'm guessing you would call this two significant figures since one revolution would be considered exact and it's over 20 seconds. So let's go with two significant figures. We're going to make this then, this should then be 310 newtons. And then this should round up to 380 newtons. That's the force that the seat is going to have to push up on the person at the top. And this is the force that the seat's going to have to push up on the person at the bottom. Now the last part of the question they ask here is, what speed is required to feel weightless at the top? Fortunately, we already have this little equation here. I'm just going to erase the rest of this stuff because I don't need any of this. I'm just going to need this portion right here. Here I've erased everything. The normal force that the seat has to push up on this child when they're at the top is going to be equal to the child's weight minus the centripetal force, or if you want to call it the centrifugal force, the force at which the person is being pushed upward by the rotation. You can look at it either way, is going to be equal to this. So if we want the normal force to be zero, in other words, you feel no weight, which means that you would be sort of floating in the air for a second. That means the normal force, the seat would also push up with you at zero. So this is equal to zero, which means this has to equal this. So I'm going to put mg is going to be equal to mv squared over r. Now in this case, child's weight doesn't matter. It's on both sides. It cancels. And we can take this r, move it to this side, erase that. Now we have this. I'll just flip those around so we don't like them on that side. It's equal to rg. There we go. I can erase this now. So now we'll just want to take rg and take the square root of it. So v is going to be equal to the square root of rg, which is equal to 10 times 9.8. 10 times 9.8 square root. Can anyone guess what that answer might be? Well, here we have about 10 times 10 square root, so that's going to be about 10. I'll just do the calculation just to come out with a little better answer. I am getting 9.899 meters per second. Of course, that's way too many significant figures. We want it to 2, which means this goes to 9.9 meters per second. So that would be the answer to this thing here, 9.9 meters per second. And we've already answered the n at the top and the n at the bottom here previously. I just erased it. So I hope that helped you with the Ferris wheel. It's one that I would suggest you rewind and see if you can do it yourself as well. If it did help, like and subscribe, and I'll see you in the next video. Bye-bye.